Good evening, and welcome back to Bedtime Talks. Tonight, on this quiet night of December 19th, 2025, as you're listening, right now, an object from another star system is making its closest pass by Earth, about 168 million miles away, moving through the dark at more than 130,000 miles per hour, something ancient, something difficult to name, after a journey of billions of years between stars, is simply drifting past us. And after tonight, it won't come back. This isn't a movie scene. It's happening in real time. So settle in, let your breathing slow, and welcome to a very special episode. Tonight, we're not only sharing the latest on 3I Atlas. Tonight, we're witnessing a small piece of history, and we'll follow the path from this moment back to the first night everything shifted. Through each discovery, each strange measurement, each coincidence that feels a little too sharp, we'll trace why 3I Atlas has become one of the most disputed and most captivating visitors we've ever recorded. And by the end, you'll understand why some scientists believe it could be older than our own solar system, why its behavior keeps raising careful eyebrows, and why the next milestone, Jupiter, in March 2026, still hangs in the distance like a question. But first, let's stay with this moment. Let's honor what's unfolding under winter skies, because for a short time, the universe has sent something close, enough for us to see, and all we have to do is look. But first, let's stay with this moment. Let's honor what's unfolding under winter skies around 0600 UTC on December 19th. An object designated 3I Atlas, also known formally as C 2025 N1, has reached its closest point to our world, a distance of 798 astronomical units. In everyday terms, that's about 270 million kilometers or 168 million miles, nearly twice the distance between Earth and the Sun, and still, this is the closest this interstellar traveler will ever be to us. Just sit with that for a breath. A body that may have wandered the void for 7 to 14 billion years has finally come near our doorstep. Not to linger, not to collide, not to deliver a message we can easily translate, only to pass through, to sweep by our star and our planets, and then fade back into the cosmic night it came from. There's something quietly heartbreaking in that, like a ship crossing a dark sea, like a stranger on a train, a brief glance, and then gone. But 3I Atlas is not an ordinary passerby. Since its discovery on July 1st of this year, it has resisted simple explanations. It has acted in ways comets shouldn't. It has shown features no one has clearly documented before, interstellar or otherwise. And it has stirred a debate that grows sharper with every passing week. So what are we seeing right now, in the hours around closest approach? Telescopes across Earth are locked on. The Virtual Telescope project in Italy hosted a live stream. Rain slowed some views, but amateur astronomers worldwide have been adding their own images, building a shared portrait of this visitor, frame by frame. Yet the most unusual perspective has come from space. Just yesterday, NASA released images captured by Europa Clipper, the probe headed toward Europa, Jupiter's icy moon. Before it reaches that distant destination, Europa Clipper found itself in a rare position, able to watch 3I Atlas from an angle we on Earth couldn't match. On November 6th, 2025, Europa Clipper's ultraviolet spectrograph watched for about 7 hours from roughly 102 million miles away. At the time, many Earth-based observations were blocked by the Sun's geometry. That makes this viewpoint truly irreplaceable. And what did it detect? Signatures of oxygen, hydrogen, and dust streaming from the comet. It observed from a sunward direction, offering a downstream look at both the dust tail and the plasma tail. Details like these are almost impossible to capture from Earth alone. Dr. Kurt Rutherford, the principal investigator for the ultraviolet spectrograph, described the opportunity as completely unexpected. His team could see gases leaving the comet and water molecules breaking apart into hydrogen and oxygen atoms. That window into the process gives scientists a deeper sense of what the comet is doing and what it's made of. Europa Clipper wasn't alone. In late November and early December, X-ray telescopes turned their gaze toward 3I Atlas, and what they found was astonishing. Japan's XSM Observatory, in partnership with NASA and ESA, observed 3I Atlas from November 26th to 28th for about 17 hours. The images revealed a halo of X-ray emission extending about 250,000 miles from the nucleus, roughly the Earth-Moon distance. This glow wasn't coming from the comet as heat. Comets are far too cold for that. Instead, it points to charge exchange. Here's what that means, gently and simply. Solar wind ions, like oxygen and carbon ions missing many electrons, collide with neutral gases released by the comet. They steal electrons, and as they settle, they release X-ray photons. We've seen this in many solar system comets, but never before in an interstellar one. So 3I Atlas became the first interstellar comet observed in X-rays. Then came ESA's XMM Newton on December Dryad 2025. It observed for about 20 hours from roughly 175 to 177 million miles away. The image showed a soft red X-ray glow against deep space, with faint gradients of purple and blue around it. X-ray data matters because it can reveal gases other instruments struggle to trace. Optical telescopes show dust and certain species. Infrared tracks molecules like water and carbon dioxide. X-rays can be especially sensitive to elements like hydrogen and nitrogen, the quiet ingredients that are otherwise hard to measure. Taken together, it suggests something important. 3I Atlas is actively outgassing. It's releasing material at a meaningful rate, with solar warmth driving sublimation just as it does for comets born in our own system. And yet, something about this object still feels different. Look closely at the imagery. 3I Atlas shows what astronomers call an anti-tail. Most comet tails point away from the sun, pushed by solar wind and radiation pressure. But this object also shows a strong feature pointing sunward, a sun-facing jet, visible since early Hubble images in July. Harvard astrophysicist Avi Loeb has discussed this at length. He notes the anti-tail appears in a Hubble image from July 21st, when the comet was still approaching, near 3 astronomical units out. And it remains visible in a later Hubble image from November 30th, as the comet was already moving away. That persistence is the part that unsettles the usual models. In Loeb's view, gas and tiny dust grains should be driven anti-solar. They shouldn't maintain a tight, sunward column. He's proposed possible explanations. In work with Eric Keto, one idea is sunlight scattering from tiny ice fragments shed from the sun-facing side, fragments that evaporate before solar pressure can push them back. Another paper, published December 8th, connects the anti-tail to a swarm of objects lagging behind, influenced by the comet's odd motion, which brings us to the phrase at the center of the controversy: non-gravitational acceleration. Motion that gravity alone cannot explain. Something is pushing this object, and the question of what has sparked intense debate. For most comets, the answer is straightforward outgassing. Jets act like tiny thrusters. That explanation is common, well-studied, almost comforting. But 3I Atlas refuses to stay comfortable. NASA officials said on November 19th that by conventional measures, it is a comet, it has a coma, it has a tail, and it releases volatiles like carbon dioxide, water, carbon monoxide, and hydrogen cyanide. By normal standards, it fits. And still, the list of anomalies keeps growing. A sunward antitail that shouldn't hold. Extreme negative polarization not seen in typical comets. A nickel-to-iron ratio, some argue, resembles industrial alloys, a trajectory aligned with the ecliptic within about 5 degrees. An arrival direction some connect to the 1977 wow signal, one improbability after another, stacked like quiet stones. And tonight, with closest approach upon us, we reach a fork in the road. We can accept the conventional explanation and let it pass. Or we can do what science asks gently, carefully, and without fear, and ask the harder questions. What is 3I Atlas? Truly, where did it begin? Why does it behave this way? And the most haunting question, is it only passing through, or does it have a reason? To follow that thread, we return to the discovery, to a winter night 6 months ago when telescopes in Chile noticed a faint moving blur among the stars. No one knew then what they'd found. No one could have predicted the storm of debate that would follow. So let's go back to the beginning, back to July 1st. 2025, when humanity first confirmed its third visitor from beyond the solar system. Because to understand where 3I Atlas may be going, we have to remember where it has been and the trail of questions it left behind. July 1st, the night everything changed. The Atlas telescope at Rio Hurtado, Chile, sits around 5,000 feet above sea level in the Atacama region, one of the driest, clearest observing environments on Earth. On that night, under exceptionally dark skies, it captured something small, faint, and world-changing. ATLAS stands for Asteroid Terrestrial Impact Last Alert System, a NASA-funded network built to scan for threats, night after night, automatically. Robotic cameras image wide swaths of sky, and software compares frames, searching for motion. That night, the system flagged an anomaly, a dim smudge around magnitude 18, drifting near the border of Sagittarius, in a crowded region close to the galactic plane, where the Milky Way's dense star fields make small moving objects easy to miss and easy to confuse with the background. That may be why it wasn't noticed sooner. Later, an amateur astronomer, Sam Dean, found hints in older data suggesting Atlas had imaged it as far back as June 5th, nearly 20 days earlier, and the Zwicky Transient Facility at Palomar had observations dating back to June 14th. But on July 1st, it crossed a confidence threshold. The software was sure enough to raise the alarm. A report went to the Minor Planet Center, the global clearinghouse for discoveries, and within hours, excitement became something heavier as trajectory calculations started to arrive. It wasn't a typical asteroid. It wasn't a comet from our own Oort cloud. The math was clear, unsettlingly clear. Its speed and path didn't match something born here. This object was moving too fast, too steep, to be a native. The velocity sealed it. About 61 kilometers per second relative to the Sun, roughly 136,000 miles per hour. No planetary slingshot could do that to an object that began inside our system. So the conclusion formed, quietly. Inevitably, it came from somewhere else. By the end of that first week, the designation became official. The International Astronomical Union named it 3I Atlas, the 3I marking the third confirmed interstellar object. After Oumuamua in 2017 and Borisov in 2019. Atlas honoring the survey that found it. But what kind of object was it? Early images were ambiguous, mostly point-like. Maybe an asteroid, maybe a quiet comet. Yet there was a faint softness at the edges, a suggestion of haze. Larger telescopes soon followed up, and on July 21st, Hubble captured an image that ended the early uncertainty. A teardrop-shaped cocoon of material, dust streaming away from a solid nucleus. A coma, the classic signature of an active comet. So this wasn't a dead rock. Geologically speaking, it was alive, shedding material as it fell toward the Sun. But Hubble also hinted at something else, even then a faint extension toward the Sun. The earliest trace of the anti-tail. Astronomers rushed to pin down basics: size, mass, composition. But the nucleus couldn't be resolved directly. So estimates depended on brightness and reflectivity assumptions. Early diameter guesses ranged widely, from about 440 meters to roughly 5 kilometers. A huge uncertainty, more than an order of magnitude. If the larger end is right, 3I Atlas would be bigger than both earlier interstellar visitors. Oumuamua may have been only a couple hundred meters long. Borisov's nucleus, around a kilometer. A multi-kilometer 3I Atlas would be a giant by comparison. Mass estimates were just as dramatic. Some calculations suggested more than 33 billion tons, far heavier than Oumuamua by an enormous margin. Whatever expelled it from its home system may have launched an immense body into interstellar space. And naturally, the next question followed: where did it come from? That question led into galactic archaeology. By analyzing velocity components, Astronomers traced its path backward. The direction pointed generally toward Sagittarius, toward the inner Milky Way's sky, not straight from the galactic center, but from a region tied to older stellar populations. Our galaxy isn't a simple flat disk. It has layers, including a thin disk where our sun lives, and a thick disk of older stars orbiting above and below the main plane. The thick disk is ancient, often 7 to 12 billion years old, stars from an era when the universe was younger, long before our solar system formed, and the incoming trajectory of 3I Atlas suggested it may have originated from that older population. Matthew Hopkins, at the University of Oxford, had been building models predicting likely properties of interstellar objects based on stellar origins. Just a week before the discovery, he defended his doctoral thesis on this exact topic. When 3I Atlas appeared, he suddenly had a real test case. His team's analysis was striking. Using a statistical framework sometimes referred to as the Oxford model, they estimated roughly a 2/3 chance that 3I Atlas is older than our solar system. Their best range placed its age between 7, 6, and 14 billion years. Pause and feel the scale of that. If that estimate holds, this comet formed around a star that ignited when the universe was still young. It may have been ejected during violent planetary rearrangements, and then wandered for eons past countless suns through quiet, dark, carrying in its ice a record of conditions from before Earth, before our Sun, before almost everything familiar. Professor Chris Lintott, a co-author and BBC Sky at Night presenter, summed it up simply. This is a visitor from a part of the galaxy we've never examined up close before, and there's about a 2/3 chance it has been drifting through interstellar space ever since its formation. Even the chemistry can be read as a clue. Cosmic rays over billions of years can transform surface ices, building carbon dioxide-rich crusts and dark, processed layers. And observations by James Webb in August reported unusually high CO2 relative to water, a pattern consistent with long-term irradiation. But age wasn't the only surprise. There was also the direction it arrived from. 3I Atlas came from the south. That might sound minor, but it ran against expectations. Many models predicted most interstellar objects would appear near the solar apex, the direction the sun is moving relative to nearby stars, near Hercules in the northern sky. Instead, 3I Atlas approached from near Sagittarius, closer to the galactic center direction, almost the opposite. That southern approach made detection harder and challenged the neat assumptions about where these visitors should come from and how often we might miss them. And as we hold that thought, we begin to understand why this story feels so vast. Because 3I Atlas doesn't just pass near Earth, it passes through our expectations, quietly asking us to look again and to keep watching. A little longer, the speed mattered too. 3I Atlas was moving faster than both Oumuamua and Borisov, but that pace, by itself, wasn't a red flag. For objects thought to come from the Milky Way's thick disk, a higher velocity is actually expected. An ancient traveler, nudged for eons by gravity, can arrive quickly, simply because it's been bumped around for billions of years. In the first weeks after discovery, there was real hope we could trace it home. Teams combed through the Gaia star catalogue, a map of precise positions and motions for billions of stars. A group led by Yang Guo reported that 3I Atlas may have passed within about 1 parsec, around 3 light-years, of 25 known stars within the last 10 million years. But on cosmic scales, 10 million years is a blink. If 3I Atlas has been traveling for billions of years, its path would have been reshaped again and again by countless distant stellar encounters. The original trek is, essentially, scrambled. We may never identify the exact star that birthed it, so we may not know its birthplace, but we can still learn what it has become. As July eased into August, observation time multiplied. Ground telescopes across continents tracked the visitor. Space telescopes carved out narrow, precious windows, and the data began to suggest a deeper mystery. 3I Atlas was releasing gas, and the blend wasn't entirely typical. On August 6th, the James Webb Space Telescope studied it with near-infrared spectroscopy. The signatures pointed to carbon dioxide, carbon monoxide, water ice, and a compound called carbonyl sulfide. The CO2 to water ratio appeared unusually high compared with many solar system comets. That part could fit an ancient story. Over vast spans of time, cosmic rays can alter surface ices, slowly converting carbon monoxide into carbon dioxide, leaving behind a chemical fingerprint of extreme age. But other clues were harder to smooth into a simple explanation. Spectra also suggested atomic nickel in the coma. Nickel alone isn't unheard of, even in our own comets. What raised eyebrows was the balance. In 3I Atlas, nickel seemed to outweigh iron in a way that felt out of pattern. Even more striking, the nickel to cyanide ratio appeared far larger than what's seen across thousands of catalogued comets, including Borisov. That anomaly drew the attention of Avi Loeb, already known for controversial interpretations of Oumuamua. Loeb argued the nickel numbers deserved careful scrutiny. He noted that nickel without iron can resemble certain high-purity nickel alloys, the kind created when refining separates nickel from iron contamination. On Earth, one industrial method is the carbonyl process, often associated with producing very pure nickel. Was that proof of anything artificial? Loeb avoided claiming certainty, but he added it to a growing set of oddities he believed should not be brushed aside. The broader community pushed back. Unusual ratios can arise naturally, especially if the parent environment was chemically uncommon or if formation processes concentrated certain metals more than we're used to seeing. And the reality was, the early data still carried uncertainties. Extraordinary conclusions require extraordinary proof. But the puzzle pieces kept appearing. By the time 3I Atlas slipped behind the Sun in late October, on its way toward perihelion, the list of questions had grown long enough to ignite a controversy that refused to cool. Through that summer of 2025, humanity watched a visitor from another star system for an extended stretch. What we saw was quietly beautiful and quietly strange. An ancient wanderer, possibly older than our world, warming under an unfamiliar sun and shedding traces of its primordial ice, like a time capsule, beginning to open. And still, the biggest surprises were waiting. Because when 3I Atlas rounded the Sun and returned to view, it would show behavior that stretched the usual definition of comet activity. Jets pointed the wrong way, polarization patterns no one could easily categorize, and a trajectory that seemed, almost too neatly, aligned. The summer of discovery was closing, and the autumn of anomalies was about to begin. A story, billions of years in the making. So close your eyes for a moment, if you can, and try to imagine 7 billion years. Not 7 billion miles, not $7 billion, but 7 billion years. When this object first gathered from gas and dust around its parent star, Earth did not exist. Our Sun did not exist. The atoms that would one day become you were still scattered across the galaxy, locked inside stars that had not yet ended, or floating as thin hydrogen in the vast dark between nurseries of light. The universe itself was younger then, barely half its current age. Galaxies were still shaping themselves through mergers. The Milky Way was more chaotic, less settled, its spiral arms less defined, its stellar populations still sorting into the thin disk and thick disk we describe today. And somewhere in that ancient era, ice and rock and metal came together around a star we will probably never name. It may have orbited for ages. Then something changed. A gravitational disruption, perhaps migrating giant planets, perhaps a distant stellar flyby, and the small body was flung outward. It reached escape speed, broke free from its star's hold, and began the long fall into interstellar night. Consider what that voyage must have felt like, because interstellar space is not truly empty, but it is close. The average density between stars is about 1 atom per cubic centimeter. The air you breathe holds roughly 25 quintillion molecules in that same volume. Between stars, the vacuum is more perfect than anything we can make in a laboratory. Through that near-nothingness, 3I Atlas drifted. Temperatures fell to only a few degrees above absolute zero. Surface ices froze solid and stayed that way for ages. Cosmic rays, high-energy particles struck continuously, slowly changing chemistry, building a processed crust. Layer by layer. Sometimes it passed near another star, not close enough to be captured, but close enough to be tugged. Each encounter nudged its trajectory like a soft, repeated tap on a drifting coin. Over billions of years, those tiny changes add up until the original path becomes impossible to reconstruct. Gaia has mapped nearly 2 billion stars. Using that atlas of motion, researchers searched for stars the object might have passed near during the last 10 million years. They found about 25 candidates within roughly 3 light-years of the reconstructed track. But again, 10 million years is only a sliver. If 3I Atlas is truly 7 billion years old, 10 million is like trying to locate someone's birthplace by reviewing only the last 2 weeks of a life spanning a century. The trail is simply too erased. So we may never point to one specific star, yet we can infer something powerful about the population it came from, and that inference begins with velocity. Astronomers describe motion with 3 components: U, V, and W, a simple language for a very large galaxy. U tracks motion toward or away from the galactic center. V follows the direction of galactic rotation, and W measures motion up or down relative to the galactic plane. Most nearby stars have modest W values. They gently bob through the thin disk. But 3I Atlas arrived with a W velocity near plus 18, 5 kilometers per second relative to the Sun. That's notably high, and it matches what we see in thick disk orbits, tilted paths, that swing above and below the galactic plane. And the thick disk is old. Its stars formed early in the Milky Way's history, often 7 to 12 billion years ago. So if 3I Atlas was ejected from a thick disk system, it likely formed around an ancient star and could be at least that old, or older still, depending on how long it drifted before being flung free. The Oxford model, developed by Matthew Hopkins and colleagues, uses statistical methods to estimate likely ages based on trajectory and galactic dynamics. Applied to 3I Atlas, it suggested a most probable range of about 6 to 14 billion years, with roughly a 2/3 chance it predates our solar system. Some work has leaned toward a middle value. A team led by Xavier Perez-Couto in Spain ran simulations involving over 13 million stars and suggested an age around 10 billion years. 10 billion years, a number so vast it needs a frame to hold it. 10 billion years ago, the universe was only about 8 billion years old. Large structures were still assembling, galaxies were still evolving into familiar forms. And in our Milky Way, the thick disk was actively forming stars, enriching space with heavy elements forged in stellar cores and scattered by supernovae. The conditions were already right for planetary systems, though early ones may have formed with fewer heavy elements than our solar neighborhood enjoys today. 3I Atlas may be a remnant from one of those primordial systems, a frozen archive, preserving chemical clues from a very old chapter of the galaxy. Webb's chemistry fits that picture in a gentle way. An elevated CO2 to water ratio can be consistent with long-term irradiation. Cosmic rays can slowly convert CO ice into CO2, building a signature that whispers age. There are also hints of long exposure to radiation on the surface, a reddish tint in some wavelengths, and possible signs of tholins, complex organics formed when simple ices are bombarded for long periods. Tholins exist on many outer solar system bodies, but on 3I Atlas, the pattern may reflect not millions of years, but billions. There's something almost reverent about realizing that. Material assembled before our sun lit up, briefly crossing our view, atoms arranged around an alien star, traveling through distances so immense it may have gone millions of years between encounters with even a stray particle. And now, briefly, improbably this traveler has entered our neighborhood. It's shedding a little of its ancient substance into sunlight, revealing secrets kept longer than Earth has existed. But age isn't only wonder. Age also widens the list of what could be possible. Over 10 billion years, even rare events eventually happen. A drifting body might pass through molecular clouds, move through changing galactic environments, and experience eras of chemistry we don't fully understand. It might even brush close enough to other systems to collect trace material thrown outward from other worlds. What if 3I Atlas carries mixed fingerprints, isotopic hints from different regions, different epochs, maybe even multiple stellar neighborhoods? If we could read the composition in enough detail, it might tell not only of its birthplace, but of its entire long voyage across the Milky Way. We're not there yet. The object is distant, and the window is short. But the possibility remains. and it pulls at the imagination. This may be more than a comet from another star. It could be a sample of galactic history itself, a natural archive written in ice. And with great age comes another implication, one that reaches beyond geology. If 3I Atlas formed billions of years ago, then it formed in a universe that had already had time for many generations of stars to live and die, time for rocky planets to form, and perhaps time for life to arise. Somewhere, we have no evidence that 3I Atlas is anything other than natural. The mainstream consensus holds to that. But Loeb and a few others argue for keeping the mind open, not leaping, but not refusing to look. If civilizations could have appeared elsewhere long ago, they might have had time to explore, to send probes, and some probes might masquerade as ordinary objects at first glance. Loeb has been careful here, not declaring certainty, but suggesting a non-zero possibility worth investigating. Even so, most of the field rejects that framing. Researchers like Jason Wright have published detailed critiques, arguing that the claimed anomalies can be natural or the result of reading too much into limited data. In science, this debate won't be resolved by persuasion. It will be resolved by measurement, and while 3I Atlas remains within reach, each observation tightens the picture. Whether it's purely natural or merely unusual, it is still unprecedented in what it offers us: a body that may predate our world, carrying ice formed before our sun ignited, shaped by an incomprehensibly long drift through the galaxy. It feels like a messenger from the deep past, from a Milky Way that was still becoming itself. And in a few years, it will likely fade beyond practical tracking, too dim, too far. Even for our strongest instruments, it will continue outward toward interstellar darkness, carrying its secrets into another long silence. But for now, in this brief window, we can study it. We can analyze its light, model its motion, and gather the fragments of story our tools can reach. Every data point is precious. Every reading is like a small word in a message that took billions of years to arrive. The ancient traveler is here for just a moment, and we are listening. And that is why tonight matters, because in the quiet of space, even a faint signal can be a doorway. What it reveals next depends on how patiently we watch and how willing we are to hold space for possibilities we haven't pictured yet. Because the story of 3I Atlas has become a story of anomalies, and in science, anomalies are where discovery begins. When the numbers won't sit quietly inside our old explanations, that's when the most important questions appear. Those gaps between prediction and reality are where new understanding is born. And 3I Atlas has offered more of those gaps than almost any comet in recent memory. By many counts, researchers have identified about 15 distinct features that strain conventional interpretations. Do they point to something truly exotic, or simply to how incomplete our knowledge of interstellar comets still is? That question is now the fault line running through the astronomical community. So let's move through them, calmly, one by one. What was observed, why it's considered unusual, and what explanations have been proposed. And by the end, you'll understand why this visitor has sparked such intense debate, and why some scientists quietly wonder if we're seeing something unprecedented in modern astronomy. The first anomaly is trajectory. 3I Atlas follows a retrograde orbit, traveling opposite the direction of the planets around the Sun. That alone isn't shocking. Roughly half of long-period comets show retrograde motion. But the orientation of this orbit is what stands out. Its orbital plane sits unusually close to the ecliptic, the same plane Earth and the other planets follow within about 5 degrees. If interstellar objects arrive from all directions uniformly, a near match like that feels statistically rare, often quoted as around 0. Bifinger, roughly 1 in 500. Why would a visitor from another star system drift in so neatly aligned with our planetary lane? Loeb has suggested this could be consistent with a chosen approach path, one that favors observation or interaction. Critics answer with a simple caution. We only have 3 confirmed interstellar objects so far. 3 samples is far too small for strong statistics. And there's another factor: detection bias. Our surveys may be better at spotting objects with certain orientations, so unlikely alignments can become more common in what we actually notice. Luck and selection effects can masquerade as design. The second anomaly is timing. The timing of 3I Atlas's path brought it close to multiple planets, while also making it difficult for Earth-based telescopes to observe the object during its most solar-intense phase. It passed within about 29 million kilometers of Mars in early October, close enough that orbiters could potentially gather valuable data. It is projected to come within roughly 54 million kilometers of Jupiter in March 2026. And then there's perihelion. Perihelion occurred when the comet was effectively hidden behind the Sun from Earth's perspective. Solar conjunction arrived only days beforehand, blocking the view right when activity might be most dramatic. Loeb has described this overall configuration as extremely unlikely, sometimes estimated below zero. Baifinger Wu. Critics respond that this style of probability can mislead. After the fact, any specific sequence can be made to sound improbable. Without a prior prediction, probability arguments lose weight. The third anomaly is size and mass. 3. I Atlas appears very large by interstellar visitor standards. Some estimates place the nucleus as big as several kilometers, with mass estimates reaching into the tens of billions of tons. If those upper numbers are right, it would dwarf Oumuamua and exceed Borisov by a wide margin. But large objects are also easier to detect. That means our surveys naturally favor giants. Even if smaller interstellar bodies are far more common, we may mostly discover the bright, massive ones. So the giant comet surprise could be a selection effect, not necessarily a sign that the object is unusual in itself. The fourth anomaly involves chemistry, especially nickel. Measurements suggest nickel appears unusually abundant relative to iron. In most natural environments, nickel and iron track together in fairly predictable proportions. Here, nickel seems to dominate, and the nickel to cyanide ratio has been described as far outside the norm, even compared to thousands of catalogued comets, including Borisov. Loeb has noted that a high-purity nickel signature can resemble what we see in industrial nickel alloys on Earth. He has referenced the carbonyl process, a method that can refine nickel and separate it from iron. Could that imply artificial processing? Mainstream researchers remain skeptical. A parent star could have unusual abundances. Formation chemistry might concentrate nickel in ways we haven't modeled well, and iron detection at these distances is difficult. Many argue we need more data before treating this as a solid anomaly. The fifth anomaly is the anti-tail. Most comets grow tails pointing away from the Sun. 3I Atlas shows a persistent sunward feature, a narrow, tightly directed jet pointing toward the Sun seen from early Hubble imagery through later observations. It appears unusually collimated, extending hundreds of thousands of kilometers and staying close to the solar direction. Traditional outgassing tends to spread material more diffusely. Loeb and Eric Coito have suggested one possibility: tiny ice grains shed from the sun-facing side that evaporate quickly before solar radiation pressure can redirect them, creating a sunward stream that is real but short-lived. Another idea, a swarm of fragments lagging behind due to non-gravitational acceleration. Others point out that anti-tails can appear in ordinary comets as a geometric effect when Earth crosses the orbital plane. The challenge is persistence. 3I Atlas's sunward feature seems to survive across changing geometry, making pure projection explanations harder to rely on, which keeps this one in the unresolved pile for many observers. The sixth anomaly concerns the rotation axis. Reports suggest its spin axis may align within about 8 degrees of the sunward direction. That orientation can matter. If a comet spins with its axis pointed sunward, one hemisphere can remain lit while the other stays dark, potentially shaping jet behavior. But here's the tension as the comet moves along its orbit. The solar direction changes. A rotation axis tends to remain fixed in space, so a tight alignment should be fleeting, yet some interpretations suggest it persisted longer than expected. Loeb has highlighted the improbability of such a match, while critics again note uncertainty in the underlying measurements and the danger of leaning too hard on small sample statistics. The seventh anomaly is polarization. 3I Atlas shows unusually strong negative polarization, described as extreme compared with known comets. Polarization reflects how light waves align after scattering, and that alignment depends on particle size, shape, and composition. Such an extreme pattern can imply unusual dust properties, and might even tie into why the sunward feature behaves strangely. But so far, no widely accepted natural explanation has closed this loop. The eighth anomaly is carbon chain depletion. Early spectra suggested reduced C2 and C3 molecules, the species that often give comets their greenish glow. Early on, 3I Atlas looked more muted, even reddish, consistent with a different mix of volatiles and surface processing. Later, post-perihelion imagery suggested greener tones, possibly as fresher material was exposed. Some researchers see this as normal evolution. Others consider the shift another puzzle piece. The ninth anomaly relates to water abundance. Measurements indicate a low water contribution relative to carbon dioxide, and while high CO2 can fit an ancient, irradiated surface. Some argue the ratio sits at the extreme edge, even for old object models. That keeps the question open age alone or additional processing. The 10th anomaly focuses on perihelion distance. 3I Atlas passed the Sun at about 1.60, just inside Mars's orbit. That's close enough for strong activity, but not so close that fragile material would be guaranteed to break apart. Loeb has argued this distance provides a kind of sweet spot, significant interaction with the inner solar system without maximal destructive heating. Skeptics counter that perihelion is simply what orbital mechanics delivered, given the incoming velocity vector, and sweet spots often appear meaningful only after we notice them. The 11th anomaly is non-gravitational acceleration. 3I Atlas's path doesn't fit gravity-only calculations perfectly. In comets, that's often explained by outgassing jetting gas acts like tiny thrusters. JPL regularly updates non-gravitational parameters as more tracking data arrive, and shifts in those estimates have fueled debate. What keeps attention here is how this acceleration interacts with the other coincidences people have pointed out. The 12th anomaly involves Jupiter's Hill radius, projected forward. 3I Atlas's approach to Jupiter in March 2026 falls near 53 to 54 million kilometers a distance, strikingly close to Jupiter's Hill radius. The region where Jupiter's gravity dominates local orbital stability. Loeb has emphasized the closeness of the match and suggested it's statistically startling. In principle, passing near that boundary could allow small debris to be captured into stable configurations around Jupiter if debris were released at the right time and speed. That's where speculation blossoms. Is it aiming for Jupiter, or is it an elegant coincidence? Most astronomers urge restraint because coincidence is common in large orbital parameter spaces. Still, Loeb argues the precision is notable enough to justify continued monitoring at minimum. And here's the quiet truth beneath all of this. Even the most conservative scientists agree on one thing: 3I Atlas is worth watching closely. Because when enough unusual features stack up, even if each has a possible natural explanation, the combined pattern becomes harder to ignore and harder to forget. The 13th anomaly lives in the light itself. 3I Atlas did brighten as it fell inward toward the Sun, just as a comet should. But the tempo of that brightening didn't sit neatly inside the curves we know from solar system comets. There were short episodes where the glow surged faster than expected, suggesting brief outburst-like bursts, followed by quieter stretches where the brightness seemed to settle again. And to be fair, comet brightness is one of the messiest things to predict. These bodies are alive with change. They can flare suddenly, then fade, then flare again, sometimes for reasons we only understand in hindsight. So the brightness quirks of 3I Atlas may simply reflect that natural volatility. The 14th anomaly, as we mentioned earlier, returns us to geometry, the reported alignment of the rotation axis with the sunward direction, a setup that can shape jets and activity, but is still strangely well-timed if it truly persists across changing orbital angles. And then we reach the 15th anomaly, the one that makes even cautious scientists pause before speaking. Because it points at least loosely toward a story from nearly half a century ago, a faint radio event in 1977 and an icy traveler arriving in 2025, two moments separated by decades, yet sometimes spoken about in the same breath. That connection deserves its own careful walkthrough. But before we step into that long corridor of history, let's take one slow breath and consider what the whole set of 15 might suggest. Any single anomaly, on its own, can often be explained away. Statistics produce coincidences. Our comet models are incomplete. Interstellar visitors are rare, and rarity alone can look like strangeness because we simply don't have enough examples to know what normal looks like out there. But what unsettles people is the way the anomalies accumulate. They don't arrive alone, they arrive as a cluster. Some argue that when multiple unlikely features appear together, the combined chance drops dramatically, as if you're multiplying small probabilities until the result approaches zero. But critics push back, and they have a point. The anomalies may not be truly independent. Several could share a single underlying cause: extreme age, unusual chemistry, uncommon dust properties, or the limits of our measurements. And statistical arguments also depend on assumptions, what we choose as a baseline, what we call rare, what we expect to see. So the math becomes part of the debate, not the end of it. Another caution is quiet but important: our priors aren't neutral. We expect interstellar objects to be different from solar system comets, so when something looks odd, we may amplify the oddness, or we may dismiss it too quickly, depending on what feels safer. That's why this dispute keeps repeating itself in papers and meetings. Not because anyone wants drama, but because the data keeps leaving room for more than one story. Still, one point remains steady. This will not be resolved by rhetoric. It will be resolved by evidence. Every new observation of 3I Atlas adds a little more texture, supporting certain interpretations, weakening others, and slowly separating what is truly unusual from what only seemed unusual at first glance. And whatever the final answer is, 3I Atlas has already forced astronomy to stare directly at questions it would rather postpone. Are we seeing a natural object with rare, exotic properties, or something outside that category entirely? And if it's something else, what could that even mean in a universe this old? Some researchers think the next clue might not be in the comet's dust, but in a direction on the sky, a place associated with a signal that has lingered in scientific memory for almost 50 years. The so-called WOW signal. A moment in time, August 15th. 1977, 48 years ago, the Big Ear radio telescope at Ohio State University was scanning the sky, listening for anything that might resemble an artificial transmission. SETI was still young then, carried by optimism, and by the dawning realization that the Milky Way holds billions of stars, many with worlds of their own. The search wasn't dramatic most nights. It was patient, repetitive, and mostly quiet. That evening, astronomer Jerry Amon was reviewing the output. Back then, the data arrived on paper, long computer printouts filled with letters and numbers, each character marking signal strength in a narrow band of frequency. Most of it was ordinary noise, the steady hiss and crackle of the cosmos mixed with the occasional human-made interference. Amon had learned to read those pages quickly. Your eyes skim, your mind filters, looking for a pattern that doesn't belong. And then, he saw it. A short sequence that rose above everything around it. 6 EQUJ 5. The intensity climbed sharply, peaked at a level so high it was marked by the letter U, then fell back to baseline. The whole event lasted 72 seconds, the exact length you'd expect from a source drifting through the telescope's fixed beam. Amon lifted a red pen, circled the strange sequence, and wrote one small word in the margin: WOW. That single note became the signal's name. And for nearly 5 decades, the WOW signal has lingered as the strongest single candidate ever recorded for a possible extraterrestrial transmission, still unexplained, still unresolved. It never returned, not once, and the details were almost too poetic for radio astronomy. The frequency was logged at 1,420, 4,550 MHz, give or take about 5 kHz. That range matters because it sits on the hydrogen line, the hyperfine transition of hydrogen, the most common element in the universe. For years, scientists had quietly wondered if a distant intelligence ever tried to whisper across the stars. Wouldn't it choose a channel every civilization could recognize, a frequency written into the cosmos itself? The signal appeared to come from Sagittarius, not far from the direction of the galactic center, and its duration 72 seconds fit the Big Ear's observing geometry perfectly. That is exactly how long a steady, continuous source would remain in the telescope's beam as Earth's rotation carried the sky across its view. In other words, the wow signal looked consistent with something artificial. Yet the universe offered no encore. Airmen and others aimed the big ear back to the same patch of sky again and again. Then other instruments joined the search. And each time, nothing. As if whatever spoke had gone silent, or drifted on, or had never been what we imagined in the first place. Theories piled up, as they always do. Satellite interference, a comet's hydrogen cloud, instrument quirks, military transmissions, even simple coincidence. But none could be proven, and most had serious flaws. So, the wow. The signal was filed into that special cabinet of astronomy, the drawer labelled unexplained, visited now and then, but never truly solved, until the story of 3i Atlas brought it back into the light. In late September 2025, Avi Lowe published a calculation that sent a quiet ripple through the community. He traced 3i Atlas backward, asking a strange question. Where would this object have been on August 15th? 1977. The answer was striking. On that date, 3i Atlas would have been around 600 astronomical units from the Sun, roughly 600 times Earth's distance, still far out, still inbound, decades away from ever brushing the inner planets. And when Lowe converted that position into a point on the sky, it landed uncomfortably close to the wow signal's reported origin. His estimate suggested the incoming direction of 3i Atlas and the wow location overlapped to within about 9 degrees, across the entire sphere of the sky. Lowe argued the odds of that kind of alignment purely by chance sit around 0.6%. About 1 inch 167. Not impossible. Astronomy produces coincidences all the time, but placed beside the growing list of other peculiarities around 3i Atlas, this added one more stone to an already heavy pile. Could the wow signal have come from 3i Atlas? It sounds like science fiction, but Lowe did what scientists do. He ran the numbers. At about 600 AU, a transmitter would need something like 0.5 to 2 gigawatts to create the detected intensity, roughly the output of a large power plant or a standard nuclear reactor. And if 3i Atlas carried technology, a gigawatt-class system wouldn't automatically be absurd. We build power systems in that range ourselves. A civilization able to launch probes between stars would almost certainly be capable of powering instruments on that scale. Even the frequency choice fits the thought experiment. If you wanted a universal calling card, the hydrogen line is the obvious place to speak. Imagine it like this: a traveler entering a new solar system, scanning for signs of life or technology, and using the most recognizable channel in nature to announce its presence. Any culture with radio astronomy would be listening there eventually, and the 72-second duration matches Big Ear's beam crossing time, at least broadly consistent with a distant source. But consistent isn't the same as confirmed. 3i Atlas was moving, not fixed. A moving transmitter could shift the timing. The observation doesn't uniquely point to a probe, it only fails to rule it out completely. And there are real problems. Serious ones. First, 9 degrees is not perfect. Close. Yes, but not exact. And both the wow, location, and 3i Atlas's reconstructed position decades earlier carry uncertainty. That overlap may be less meaningful than it feels. Second, the geometry is trickier than a simple arrow on a star map. We're comparing a historical pointing direction to a backward projection along a moving trajectory. If 3i Atlas emitted the signal while inbound, its apparent sky position and beam geometry wouldn't be a simple dot in Sagittarius story. The alignment can mislead if treated too casually. Third, and most importantly, the wow signal never repeated. If this were a beacon meant to be noticed, why speak only once? Why fall silent for 48 years? A true attention-getting beacon would likely repeat. Again and again. To increase the chance of detection. Unless it wasn't a beacon. Maybe it was a targeted transmission aimed somewhere else, and Earth simply drifted into the line of fire for 72 seconds. In that case, it wouldn't need to repeat for us. Or perhaps the emission was automatic triggered only under specific conditions. A location, a magnetic environment, a threshold event, something that hasn't happened again until the object entered our system. Or, the simplest possibility, the connection is nothing more than a coincidence. we're tempted to decorate with meaning. Most mainstream researchers lean firmly toward that last explanation. They argue the WOW Atlas link is speculative at best and potentially misleading. They point out how easy it is to find low-probability overlaps after the fact, especially when we're searching for patterns. And so far, there is no direct evidence connecting the two. But then, in October 2025, something happened that gave the discussion fresh oxygen. On October 24th, the Meerkat radio telescope in South Africa reported a radio detection associated with 3I Atlas. Now, before the imagination runs away, we need to be very clear. This was not a coded message, not a beacon, not a deliberate broadcast. What Meerkat picked up was a natural OH line hydroxyl, the familiar radio fingerprint formed when water molecules break apart under ultraviolet light. For conventional comet science, that's valuable. It supports the idea that 3I Atlas is actively outgassing water and that sunlight is dissociating it into fragments we can detect at radio wavelengths. The hydroxyl detection helped round out the picture radiochemistry alongside optical dust and infrared molecules. But for those hoping for a dramatic hello, it was both tantalizing and disappointing. The comet was now audible to radio telescopes, but what we heard was ordinary physics, not intention. Still, the mere fact that radio instruments were now paying close attention revived interest in the WOW question. Abel Mendes, from the Planetary Habitability Laboratory in Puerto Rico, announced plans to reanalyze the WOW signal with updated methods aiming to sharpen what we know about its properties and origin, and to test whether any connection to 3I Atlas is even remotely plausible. Meanwhile, Lowe continues to encourage targeted listening near the hydrogen line itself, because if 3I Atlas ever produced even a faint emission around 1,420 megahertzes, that would change the conversation instantly. So far, nothing like that has been confirmed. But let's sit quietly with the meaning for a moment and imagine only as a thought experiment what it would imply if the link were real. If 3I Atlas truly transmitted the WOW signal in 1977, then it isn't merely an interstellar comet. It would be an artifact, a probe, a beacon, something built to travel and operate across decades. Maybe centuries. Maybe longer. Its passage would no longer feel random. It would feel chosen, and the implications would be immense. Not just for astronomy, for humanity. Proof that we are not alone. Proof that intelligence can move between stars. And then the questions would arrive like waves. Who sent it from where? What is it doing here? Is it observing or interacting? Are there more travelers like it? These are the kinds of questions that can reshape a species' sense of itself. And right now, they still hang on a thin thread, intriguing, unsettling, and not yet strong enough to carry certainty. A 9-degree overlap and a probability hovering around 1%. That alone is not a verdict. It's a reminder. Science asks us to move slowly, to doubt our own excitement, because extraordinary claims demand extraordinary evidence, and we are nowhere near that bar. The WOW signal is still unsolved, and 3I Atlas is still unusual, but any bridge between them remains. For now, only speculation. And yet, there is still value in tracing that speculative line, because when we seriously test a bold idea, even gently, we sharpen our sense of what would confirm it and what would quietly dismantle it. We learn what measurements matter most. We decide where to point our antennas, which frequencies to monitor, what patterns would count as meaningful, and what would simply be noise wearing a familiar mask. Staying open does not mean believing. It simply means we don't lock the door too early. The WOW signal appeared for 72 seconds, then slipped back into silence. 3I Atlas will drift through our solar system for only a few months, and then it, too, will fade into interstellar night. Both are brief windows, unrepeatable moments that open and close, perhaps forever. If they share a cause, then we have a once-in-history opportunity to study the possible source of a decades-old mystery while it is still close enough to watch. And if they don't, we lose nothing by asking carefully. Either way, the coincidence has a strange gravity. A signal in 1977, an interstellar visitor in 2025, half a century apart, yet arriving from nearly the same region of sky. as if the universe enjoys leaving breadcrumbs in places we can't ignore. The cosmos is vast, and it is endlessly strange. Sometimes a coincidence is just a coincidence, and sometimes it is the first faint outline of a deeper pattern we haven't learned to see, as 3i Atlas continues outward, carrying its secrets with it. The WOW signal remains filed under unexplained, waiting for the day someone finally settles it. Maybe that day will never come. Or maybe the answer has been sailing through our neighborhood all along, close enough to measure, too far to touch, and too easy to misread. So we keep doing the only thing we can do. We keep watching, we keep listening, and we keep asking questions, even when the answers feel impossibly distant. And then there were the close encounters: Mars, Venus, and the spacecraft that turned their eyes toward a visitor from another star. On October 3rd, 3i Atlas swept within 29 million kilometers of Mars, the closest planetary pass of its inner system journey. Close enough for Martian assets to gather meaningful images. Close enough for Mars's gravity to bend its path, ever so slightly. Close enough that if anything unexpected happened, a fragment, a flare, a sudden change, robotic eyes would have recorded it. And they were ready. In the weeks around the flyby, a rare coordination took shape. European orbiters, American orbiters, and even surface instruments joined the campaign. ESA's Mars Express and the ExoMars Trace Gas Orbiter, often shortened to TGO, both received commands to observe the interstellar comet during its closest approach. TGO carried a sharp-eyed camera built to study Mars, but a camera is a camera, and space is open sky. So it pivoted toward the comet. The result was not a crisp portrait, even at its closest. 3i Atlas was still millions of kilometers away, but it was the closest space-based look we'd ever had of an interstellar object. A soft point. Yes, but a soft point with structure, a visible coma, hints of jets, the same features Earth telescopes have been trying to tease out through atmosphere and distance. Mars Express attempted its own observations with its stereo camera. Some exposures were less than ideal, and the comet was difficult against the star field, but even partial attempts matter in campaigns like this. They fill gaps. They strengthen geometry. They add another independent angle on the same target. NASA's Mars Reconnaissance Orbiter, with its powerful high-rise camera, joined in as well, around October 2nd. MRO captured frames from roughly 19 million miles away. Again, no cinematic detail, but clear enough to refine the comet's position and improve trajectory fits. And that is where the real power of these images lies, not in beauty, but in precision. Every accurate position measurement tightens the comet's predicted future like a drawn string. There was, however, a familiar frustration. Some Mars mission data wasn't released immediately, which sparked predictable rumors, the idea that something must be hidden. But the more grounded explanation appears: simpler processing pipelines, scheduling, and bureaucratic delays. Eventually, the observations entered the record, and the sensational theories found no firm footing. China also contributed. Tianwen's, in orbit around Mars, turned instruments toward 3i Atlas and added its own images to the growing archive. Multiple agencies, multiple platforms, all watching the same small visitor from different vantage points, a quiet demonstration of how global curiosity can synchronize when the sky offers a rare event. And then there was the moment that still feels surreal: a robot on the Martian surface, Perseverance. Sitting inside Jezero crater, raised its gaze and attempted to photograph an interstellar comet. Mars has an atmosphere thin, but not empty, and it creates just enough glow to challenge faint sky targets. Still, Perseverance managed it. A machine we built on another planet, capturing a traveler from another star. If anything can make the universe feel intimate, it's that. The Mars encounter mattered for more than sentiment. Close passes let gravity do what it always does: bend a trajectory. By measuring that bend precisely, researchers can improve estimates of the object's path, and sometimes even constrain mass and non-gravitational forces indirectly. And that leads us back to the phrase that keeps returning like a refrain: non-gravitational acceleration. Before Mars, trajectory fits assumed a certain pattern of outgassing thrust. After Mars, the observations tested those assumptions against reality. The outcome supported what many teams already suspected. 3I Atlas did experience non-gravitational effects, but pinning down the exact magnitude was difficult. Different assumptions, how thrust scales with solar distance, how activity turns on and off produced different projections. And in those projections, one controversial coincidence reappeared: the predicted March 2026 approach to Jupiter, lining up suspiciously close to Jupiter's Hill radius. But here we must breathe and remember, small uncertainties compound. A subtle change in assumed acceleration can shift a distant encounter by millions of kilometers. What looks like a perfect match today might soften into an ordinary near miss tomorrow. As the dataset improves, beyond Mars, other spacecraft join the story. NASA's MAVEN used ultraviolet instruments to track hydrogen around the comet, evidence of water molecules being broken apart by sunlight. It harmonized neatly with Meerkat's hydroxyl detection, different methods, same underlying chemistry. There were also serendipitous alignments. NASA's Psyche spacecraft passed relatively near in early September, not built for comet studies, but still carrying cameras that could, in principle. Add another point of view. ESA's JUICE mission on its way to Jupiter found itself in a favorable geometry too, and observed 3I Atlas between November 2nd and 25th, right after perihelion, when activity and structure were easiest to catch. JUICE's angle differed from Earth's, and that matters. A tail can look different when you shift perspective. A coma can hide features from one line of sight and reveal them from another. Even faint hints of multiple tail components become more trustworthy when they repeat across geometry. NASA's Lucy mission added distant frames as well, the comet a dim smudge from far away, but still useful for context and tracking. And as perihelion approached, solar missions became accidental witnesses. Stereo captured the comet in its wide fields. Punch followed its tail behavior through solar wind-dominated regions, and then quietly, almost reluctantly, SOHO, watching the Sun from L1, caught the comet near perihelion after careful stacking and processing. A faint streak against the solar corona, a visitor from another star briefly traced beside our own, taken together. The campaign was extraordinary. Ground telescopes, space telescopes, Mars orbiters, a rover on Mars, interplanetary probes, solar observatories, a whole solar system of instruments catching whatever photons they could from a once-in-a-lifetime traveler. And Europa Clipper's released observations added yet another piece, a rare sunward perspective that Earth could not provide. So, what have we learned? First, 3I Atlas really does behave like a comet in the broad sense. A nucleus, a comma, tails, outgassing signatures including water and carbon-bearing volatiles. It brightens toward the Sun and fades outward, the familiar arc of cometary life. Second, it's not a typical one. Some reported traits, the persistent sunward feature, odd polarization behavior, unusual abundance ratios, and the geometry debates keep returning across independent observers. That doesn't prove anything engineered, but it does suggest something about this comet is different, even if the explanation is still waiting behind the curtain. Third, through all of these planetary passes, it did not fragment. It did not sharply change course. It did not do anything that forced a reclassification overnight. In every encounter, Mars included, it moved like a small body should, quietly, steadily, almost indifferent, as if the solar system was simply another stretch of ocean to cross. And that matters, because if one entertains exotic possibilities, Mars would feel like an obvious moment for action, a world with history, a world we study intensely, a world we may one day inhabit. Yet nothing dramatic happened. 3I Atlas was photographed, measured, modeled, and it continued on its way. Does that prove it's natural? Not definitively. A passive probe could observe without revealing itself. A dormant system could wait for triggers we don't understand. And our assumptions about what another intelligence would do are, at best, guesses. But the simplest explanation still carries the most weight. We are watching an unusual comet, and we are still learning how strange natural can look when the visitor comes from a part of the galaxy we've never sampled this closely before. An advanced probe, if it existed at all, might be built for silent, passive watching, gathering data without leaving a clear footprint behind. It could be asleep, waiting for conditions, thresholds, or triggers we don't yet know how to recognize. Or it may simply have no interest in Mars, not in the way we imagine a distant intelligence would. And yet, when the story is still uncertain, the simplest explanation is usually the one that holds the most weight. 3i Atlas, then, is most likely what it appears to be, an interstellar comet, an ancient traveler from another star, passing through our neighborhood by chance. Its strange behaviors may still have natural causes we haven't identified yet, or haven't learned to measure properly. And the coincidences in its path may be just that, coincidences, magnified by the human tendency to search for patterns in the dark. That is why the language stays cautious, probably, likely, perhaps, not because scientists are timid, but because certainty has not arrived. Even now, observations keep stacking up, and with every new data point, the portrait of 3i Atlas sharpens. What comes next will test that picture again. Jupiter is waiting in March of 2026, and between now and then, ground-based telescopes will keep watching as the comet slowly dims and slips toward the colder, outer night. For now, the spacecraft have done their part. Mars orbiters, solar sentinels, interplanetary probes, each one adding its own pixels, its own photons, to a shared record. When the history of 3i Atlas is written, this chapter will remember something remarkable, that humanity gathered its robotic eyes across the solar system to study a visitor that came from another sun. We may not have every answer, but we asked the questions. We looked, and in science, that is always the first step. And then, almost quietly, another mystery rose into view. A mystery you can see with your own eyes. A color story that seemed to shift when it shouldn't, from red to green to gold. There is something almost spell-like about watching a comet change color, a reminder that these bodies are alive with chemistry as ancient ices meet modern sunlight. When 3i Atlas began to drift in appearance from red toward green and then toward a warmer, golden tint, astronomers paid attention, because color is not decoration in astronomy, it is evidence. It can hint at composition, erosion, and layers being exposed over time. So we begin with the first shade, the red. In the earliest detailed views, the coma carried a noticeably reddish cast, subtle, but distinct. Images from the Gemini South Telescope in Chile, shared in early September 2025, made it easier to see. The glow around the nucleus wasn't the familiar emerald tone many comets develop. It was warmer, earthier, almost organic in character. In comet science, redness often points to tholins, complex organic molecules produced when simple ices and gases are processed by radiation for long periods. We see tholins on worlds like Titan and Pluto, where relentless cosmic rays and ultraviolet light slowly cook surface materials into darker, reddish organics. For 3i Atlas, that red tone made sense. If it truly formed billions of years ago, long before our solar system, then it would have spent an unimaginable span of time under cosmic ray bombardment, building a heavily processed outer skin, rich in radiation-altered compounds that tint the coma with that faint red glow. The red also fit another early clue, a puzzling result from spectroscopy. Some observations suggested 3i Atlas was depleted in carbon chain molecules including C2, the diatomic carbon that gives many comets their classic green shine. If the surface was dominated by ancient, irradiated material, then the fresh ices that usually produce those carbon chain signatures might have been buried deeper, sealed beneath an organic crust. But comets are not static. As they fall toward the sun, they shed their outer layers and reveal what has been hidden underneath. As 3i Atlas approached perihelion, solar heating intensified, and the old processed surface began to give way, exposing a different kind of material below. In early September, during observations made around a total lunar eclipse from Namibia, amateur astrophotographers captured images that surprised many viewers. The comet looked greener, even with a faint bluish edge. Through blue and green filters, the coma appeared gas-rich and bright, as if the object had shifted from a rusty ember into something more emerald and alive. and green in comets has a well-known origin. It often comes from C2 molecules that absorb ultraviolet sunlight and re-emit part of that energy as visible green light. This is fluorescence, a familiar process in comet physics, a brief glow created when sunlight breaks down carbon-bearing ices, allowing free carbon to recombine into C2 for short moments before it is destroyed again. But that returns us to the puzzle. If earlier spectra suggested carbon chain depletion, where was the C2 coming from now? One possibility is that the depletion was only skin deep, limited to the outermost layers that had been baked and processed by interstellar radiation. Beneath that, fresher ice could still hold the ingredients needed to produce C2. As the sun stripped away the old crust, the green glow could finally emerge. Another possibility is layering, a kind of internal patchwork. If 3I Atlas formed in one environment, spent time in another, and then drifted for billions of years through interstellar space, its interior may not be uniform. Different regions could carry different chemistries, revealed in sequence, as heat and erosion work inward like a slow, patient drill. After perihelion, the green became harder to ignore. By late November, images from Gemini North showed a noticeably greener coma than the comet had displayed months earlier. Reports associated that color with diatomic carbon emission, consistent with a shift toward more typical cometary fluorescence as deeper, less processed material reached the surface. By then, 3I Atlas had swung around the sun and begun its outbound journey. The perihelion passage had been intense. Solar radiation heated the sunward face, driving strong outgassing, expanding the coma, stretching the tails, and pushing the comet's visible character away from the red of ancient organics toward the greener signature of active gas release. And then, a third shade entered the conversation, in mid-December, just days before its closest approach to Earth. Some observers reported a warmer tint, a yellowish or golden cast to the coma. A few media outlets repeated the claim, describing a shift from red to green to gold. Whether or not those reports captured the true physical picture, the question is still worth exploring carefully. What could create a golden tone? A natural answer is changing mixture. As a comet moves away from the sun, activity doesn't stop all at once. The nucleus retains heat absorbed near perihelion and continues to vent gas even as sunlight weakens. But the dominant ices can change with cooling because different volatiles sublimate at different temperatures. Early on, the most volatile species can dominate. As cooling progresses, water can contribute more strongly relative to those highly volatile ices, and dust can play a larger role in scattering sunlight. Different molecules and dust grains reflect and emit light in different ways, and under some filter combinations, a dustier, changing coma can look faintly golden, especially when the balance between gas emission and dust reflection shifts. Yet there is another interpretation, one that feels quieter and more sobering. Some researchers have wondered whether a sequence like red to green to gold might hint at depletion, successive layers being stripped away, each with its own chemistry, until the comet begins to lose the easy fuel for its glow. If so, 3I Atlas could be moving gradually toward dormancy, from an active comet into something closer to a spent, dusty nucleus. This is not unusual in principle. Many comets, after repeated close passes to a star, exhaust their accessible ices and become inactive, eventually resembling dark asteroids more than bright comets. And because 3I Atlas may have spent an extreme length of time in interstellar space, its ice budget near the surface might already be compromised, with cosmic rays converting some compounds into less volatile forms long before it ever met our Sun. The 2025 perihelion passage would then act like a final shock, a burst of heating that strips and rearranges surface layers quickly. Still, we must be honest. This is speculation. We do not yet know how much ice remains inside 3I Atlas, or how deeply its reservoirs are sealed beneath crust and dust. The nucleus could still hold vast reserves that might awaken again if it ever passes close to another star in the far future. Or it could be thinning out, releasing the last accessible volatiles from a system we will never name. And even the color story itself is not beyond debate. Some scientists caution that apparent color changes can be misleading. Different filters, different sky conditions, and different image processing choices can shift the perceived hue dramatically. Comets are faint, diffuse objects woven into messy backgrounds of scattered light and noise. Reliable color measurement requires careful calibration, something not always present in informal, widely shared images. The mainstream view, in broad strokes, is simpler. The comet did appear redder early on and greener after perihelion, even if the details of gold remain uncertain until fully calibrated data confirms it. But regardless of the exact shade at any given moment, the underlying message remains clear. 3i Atlas is changing quickly as it interacts with our Sun. The surface that greeted us in July is not the same surface we met in December. Layers have been removed. Hidden ice has been exposed. A crust built by billions of years of interstellar processing is being peeled back, revealing whatever primordial material has been protected beneath it. In that sense, the comet is running a quiet geology experiment for us, not by intention, but by physics. Each pulse of outgassing is like a slow drill through time. Red, the ancient surface. Green, fresher layers below. Gold, if it proves real, perhaps another threshold entirely. A hint that we are nearing the deeper structure of the nucleus itself. And we won't be able to watch this experiment forever. 3i Atlas is moving outward, cooling steadily. Activity will decline. The coma will thin. Eventually, the comet will slip beyond even the reach of our best instruments. But for a short season, we had front row seats, watching sunlight strip away history that took billions of years to form. Layer by layer, color by color, chemistry in motion, geology on a cosmic scale. A reminder that even the oldest travelers are not frozen in time, that the universe keeps changing and keeps offering mysteries to anyone willing to look gently and carefully for long enough. Red was the past. Green was the present. Gold might be the future, a future where 3i Atlas finally quiets, its accessible ices spent, drifting as a dark, silent husk through the endless cold. Or perhaps not. Perhaps beneath the gold, there is more ice, more color, more surprises waiting. We won't know unless we keep watching. And as long as the comet remains visible, that is exactly what we will do. And now, let's open a different window entirely, a window the human eye cannot see. X-rays, the high-energy light that reveals the invisible boundary where the solar wind meets comet gas, like a quiet storm of particles and fields. When you watch a comet from a backyard telescope, you see sunlight and glow, beautiful, but incomplete. To understand what the comet is doing in its extended atmosphere, you look beyond visible light. X-rays reveal the violent side of the interaction, the collisions and exchanges that happen where charged solar particles strike neutral cometary gas, a silent battle written in energy instead of sound. And in late 2025, two of the world's strongest X-ray observatories turned toward 3i Atlas, capturing the first X-ray views ever made of an interstellar comet. The first detection came from Japan's X-RISM mission, a collaboration with NASA and the European Space Agency. X-RISM X-ray imaging and spectroscopy mission launched in September 2023, carrying some of the most sensitive X-ray instruments ever flown. Between November 26th and 28th, Liangtianling Arshiwu, X-RISM carried out a target of opportunity observation. Its soft X-ray imager watched the comet for about 17 hours, collecting enough photons to build a meaningful picture. And what emerged was extraordinary. A diffuse halo of X-ray emission extended roughly 400,000 kilometers from the nucleus, about the distance between Earth and the Moon, a vast sphere of invisible light, surrounding an object too cold to produce X-rays by heat alone. Because comets do not shine in X-rays the way hot stars do. Even near perihelion, the surface of a comet remains far below the temperatures needed for thermal X-ray emission, so this glow had to come from something else. Something that happens when the sun's wind touches the comet's breath. That something is charge exchange. The solar wind is a steady stream of charged particles, mostly protons and electrons, flowing outward from the sun at hundreds of kilometers per second. Mixed into that stream are heavier ions, atoms like oxygen, carbon, and nitrogen stripped of many of their electrons by the extreme conditions of the solar corona. Those highly charged ions are eager to reclaim electrons. When they slam into neutral molecules released by the comet, they can steal electrons in a sudden, Energetic exchange. The captured electrons drop into new energy levels, and as they settle, they release energy as X-ray photons. This process, discovered in comet observations in the late 1990 seconds, creates a characteristic soft X-ray glow wherever solar wind meets a comet's neutral gas. The brightness and size of that glow depend on how much gas the comet is releasing and how dense the solar wind is at that location. For 3I Atlas, the X-rism halo confirmed active outgassing at meaningful rates, with neutral molecules, especially those tied to water, and its dissociation products streaming outward and interacting with solar wind across an enormous volume. And X-rism provided more than an image. Its high-resolution spectrometer can separate incoming X-rays by wavelength, revealing which ions are responsible for the emission. In the spectral data from 3I Atlas, signatures associated with carbon, nitrogen, and oxygen appeared exactly what comet scientists would expect from charge exchange between the solar wind and common cometary gases. Even at perihelion, the surface of 3I Atlas would only reach a few hundred Kelvin, warm, but nowhere near the millions of degrees required to generate X-rays directly. So the glow was not heat, it was interaction, a process called charge exchange. And to understand charge exchange, picture what happens when the sun's wind collides with a comet's breath. The solar wind is a ceaseless river of charged particles, mostly protons and electrons, streaming outward from the sun at hundreds of kilometers per second. And mixed into that flow are heavier ions, oxygen, carbon, nitrogen atoms stripped of most or all of their electrons by the fierce temperatures of the solar corona. They travel like bare, electrified skeletons, carrying an intense appetite for charge. These highly charged ions are desperate for electrons. When they meet neutral gas molecules released by a comet, they snatch electrons to fill their empty shells. On the atomic scale, it's a violent exchange, a sudden theft that leaves both the ion and the molecule briefly excited, unstable, energized, shimmering with potential. Then the new electron settles into a lower, more stable orbit, and as it drops, it releases the excess energy as an X-ray photon. This is charge exchange, first recognized in comet observations in the late 1990 seconds, and now seen again. Written across space as a soft X-ray halo, wherever the solar wind meets the neutral gas of a comet's coma. How bright that halo becomes and how far it spreads depends on two things: how much gas the comet is releasing and how dense the solar wind happens to be at that location. For 3I Atlas, the X-rism observation confirmed strong activity. The extended X-ray envelope suggested a wide outflow of neutral molecules, especially water vapor, and the fragments it breaks into expanding from the nucleus and colliding with solar particles across a vast region of space. And X-rism offered more than a picture. Its Resolve instrument performs high-resolution X-ray spectroscopy, splitting the incoming X-rays by wavelength to identify the ions producing them. In the spectrum of 3I Atlas, researchers saw signatures consistent with carbon, nitrogen, and oxygen ions, exactly what you'd expect when solar wind ions exchange charge with ordinary comet gases. In other words, in X-rays, the interstellar visitor behaved like a comet should. About a week later, the European Space Agency's XMM Newton Observatory took its turn. Launched in 1999, XMM Newton remains one of the most capable X-ray telescopes ever built. Its EPIC camera can detect faint X-ray sources with exceptional sensitivity over a wide field, like a lantern designed for the invisible. On December Driad, downtilling Arshawu, XMM Newton spent close to 20 hours observing 3I Atlas. The resulting image is strangely beautiful, almost haunting. Against a black background that represents the near absence of X-rays, a bright red point marks the comet's core, and around it, soft gradients, purple fading to blue, map a steady fall-off in intensity, like ripples spreading from a stone dropped into a dark, silent lake, far from stopping near the nucleus. The glow extends outward, tracing the boundary where comet gas meets the streaming solar wind. At the time, 3I Atlas was roughly 175 to 177 million miles from the spacecraft, with a heliocentric distance near 9 astronomical units. It had passed perihelion about 5 weeks earlier and had begun its long outbound drift toward the cold. Yet it was still X-ray bright. Even as sunlight weakened with distance, outgassing had not dropped away sharply. And charge exchange continued wherever the expanding coma offered neutral gas to the solar wind. It's a reminder that comet activity lingers not as a switch, but as a slow fading ember. With XRISM and XMM Newton separated by about a week, researchers gained something precious, a way to track change. As the comet moved outward and cooled, the X-ray signature should weaken. By comparing both datasets alongside ongoing ground-based monitoring, scientists could estimate how quickly the charge exchange region was shrinking and how rapidly the comet's activity was declining. These detections matter for several reasons. First, they show that the same physical processes we see in solar system comets also operate in an interstellar comet. That may sound obvious, but it was never guaranteed. 3I Atlas formed under another star, in another chemical neighborhood, and still, the X-ray behavior looked familiar, suggesting that in this band, at least, the visitor is made of recognizable stuff. Second, X-rays can reveal information that other wavelengths struggle to access. Optical and infrared tools excel at certain molecules: water, carbon dioxide, organics, but can miss or poorly constrain lighter, simpler species, and the full ion environment. Because charge exchange depends on the solar wind's ion mix, X-ray observations can indirectly probe parts of the coma's composition and interaction physics that remain subtle elsewhere, especially in the presence of hydrogen-related fragments and nitrogen-linked processes. Third, X-ray brightness helps constrain gas production. The more neutral gas available, the more opportunities for charge exchange, and the brighter the halo becomes. By modeling intensity and folding in what we know about the solar wind at that time, researchers can estimate how much material the comet was releasing. Early analyses suggest 3I Atlas was outgassing vigorously during these observations, consistent with its bright coma and long, structured tails seen in visible light. Fourth, and perhaps most intriguingly, X-rays offer geometry. The emission is strongest where the solar wind is dense and where comet gas is concentrated. So by mapping X-ray intensity across the coma, scientists can infer the shape and direction of the outflow in 3 dimensions, a kind of invisible topography drawn in high-energy light. And this is where another mystery begins to brush against the X-ray story: the anti-tail. If material truly streams sunward against expectation, then any neutral gas in that stream should also participate in charge exchange. X-ray data could help decide whether the anti-tail is mostly neutral gas, which might glow faintly in X-rays, or primarily dust, which would not. The analysis is delicate and still ongoing because the signal is faint, and space telescopes must sift it from background noise and unrelated cosmic X-ray sources. Extracting clean results demands careful calibration and patient statistics. But the early picture is steady. 3I Atlas glows in X-rays the way comets do. The halo stretches hundreds of thousands of kilometers, and the spectral fingerprints match charge exchange with ordinary comet gases. In the X-ray world, at least, the interstellar visitor looks almost comfortingly familiar. There's something quietly philosophical in that. X-rays are invisible to the human eye. No matter how dark the sky, you could never look up and see this halo yourself. It exists beyond our senses, accessible only through machines we have built and placed above the atmosphere, in orbit, listening for light we cannot perceive. For months, ever since 3I Atlas entered the solar wind, that emission was likely happening, unseen, unrecorded, like a signal with no receiver. And then XMM Newton looked, and the invisible became data. We glimpsed an interstellar ghost wrapped in high-energy light, a halo born from the marriage of alien gas and solar particles. And what did that halo tell us? Not that the comet was unnatural, not that it was a machine, but that it is built from ordinary ingredients: ice, dust, simple molecules releasing water and carbon compounds the way comets in our own system do. It suggests stellar winds behave like stellar winds everywhere, and the same equations apply even to a traveler that may be older than our world. We might have hoped X-rays would uncover something wildly strange, some signature that separated 3I Atlas completely from the comets we know. Instead, The X-ray story is almost soothing in its consistency, ancient, interstellar, surrounded by debates in other wavelengths, yet still obeying the familiar physics of a comet warming near a star. And this glow will not last. As the comet recedes, outgassing will weaken, charge exchange will fade, the halo will shrink into silence. Soon, 3i Atlas will return to being a dim, cold wanderer, moving through the dark with no visible aura at all. But for a brief season in late 2025, we saw what our eyes could never show us. We saw the hidden violence inside the beauty atomic collisions behind the soft haze, the universal physics that ties our sun to every other sun. X-ray eyes on an interstellar ghost, and what they revealed was strangely, wonderfully, ordinary. And now, we turn back to the visible sky, to a mystery that feels almost wrong at first glance, because there is something unsettling about a comet that points toward the sun. Everything we learn in comet science tells us tails should stream away, pushed by radiation pressure and the solar wind. Carried outward like a banner in a relentless storm, dust and gas released from a nucleus should be swept back, forming the classic tail that has inspired awe for centuries. Yet from the earliest sharp images, 3i Atlas displayed a feature pointing the other way, a persistent sunward structure, tight, narrow, and stubbornly present. The anti-tail appeared in Hubble observations on July 21st. When the comet was still inbound, beyond the orbit of Mars, and already it looked like a spike of brightness reaching toward the solar direction. That alone was unusual. In many solar system comets, anti-tails can appear briefly due to geometry, a perspective effect when Earth crosses the comet's orbital plane and dust behind the nucleus aligns in our line of sight. Those are optical tricks. They come and go as angles change. But 3i Atlas did not behave like a trick of perspective. The sunward feature lingered through months of changing geometry, showing up again and again in observation after observation. It was still present in Hubble images from November 30th, when the comet was outbound, nearly 2 astronomical units away. So whatever this was, it seemed physical, not simply visual. The collimation deepened the puzzle. In images from both amateurs and major observatories, the sunward jet looked remarkably narrow, holding a tight beam out to hundreds of thousands of kilometers. Most comet ejecta spreads and blurs with distance. A structure that stays so collimated suggests either unusual particles or unusual conditions, or a mechanism we haven't fully pinned down. Avilo focused on this mystery in detail. In work with Eric Quito, he proposed a model involving tiny ice-rich grains shed from the sun-facing side of the nucleus. In this picture, outgassing on the illuminated hemisphere lifts small particles and initially pushes them outward along the local surface normal, which, on the sunward side, points toward the sun. For a brief time, those grains could move sunward, carried by expanding gas. Then radiation pressure would begin to fight back, pushing them away and sweeping most into the conventional tail. But if the grains are extremely small, or short-lived, they might sublimate before the sun can fully reverse their motion, creating a transient stream that appears sunward, a narrow feature that can look like a jet aimed in the wrong direction. It's a clever explanation, grounded in known physics, and yet the persistence and sharpness of the anti-tail keep the debate alive, because 3i Atlas does not simply show a sunward feature once, it shows it again and again, as if the comet is insisting we keep looking at the part of the story that doesn't quite fit our expectations. Gas and dust from a comet usually bloom outward, spreading into a soft, widening fan as they leave the nucleus. So, the anti-tails narrow. Disciplined column felt unusual, as if something were guiding it, or as if the particles themselves refused to scatter. Avi spent long hours with this puzzle. In work with Eric Quito, he proposed a simple, testable idea, that the anti-tail could be made of tiny ice grains shed from the sun-facing side of 3i Atlas. In that model, the grains aren't drifting the wrong way by magic. They are launched sunward by the comet's own breathing. Here's the mechanism. When sunlight strikes the comet's day side, it warms the surface, and frozen volatiles sublimate directly into gas. That gas expands rapidly, and in the rush outward, it can lift dust and small particles with it, like a sudden gust lifting sand. the expansion tends to shoot outward perpendicular to the surface, and on the sun-facing hemisphere, outward points toward the sun, so the smallest grains can begin their journey sunward, riding the outflow like leaves caught in a fast wind. Then solar radiation pressure starts to push back. For most ordinary dust, that push is strong enough to reverse the motion quickly, sweeping particles into the familiar tail that streams away from our star. But the smallest ice particles may not behave like rocky dust. Ice can be reflective, sometimes partially transparent, and depending on grain size, is structure and composition. The radiation pressure acting on them may be reduced compared to darker, denser dust. If that push is weaker, the grains can continue sunward longer, not indefinitely, just long enough to leave a visible, narrow stream before the sun wins and turns them around. And there's a second twist. Ice grains don't last. As they move inward and warm, they shrink, sublimating away molecule by molecule until they vanish entirely. So a population of tiny ice grains could create a sunward feature that disappears before radiation pressure has time to fully redirect it. In that picture, the antitail is a steady-state illusion of renewal, fresh grains constantly launched, constantly fading, a stream maintained by ongoing ejection and ongoing loss. It's plausible and frustratingly hard to prove. At these distances, no telescope can pick out individual grains. All we can measure is the combined scattering of sunlight, the collective glow of countless particles behaving as a population, and compare that glow to what models predict. But there is another explanation that ties the antitail to a deeper controversy: the comet's non-gravitational acceleration. If 3I Atlas is being pushed away from the Sun, as JPL's trajectory solutions suggest, then anything that breaks off the nucleus might not surge forward. It could lag behind. A swarm of fragments or debris released during an outburst could remain where it was, while the main body slowly accelerates away from it. From our viewpoint, that lag could appear as material pointing sunward, not because it's moving toward the Sun, but because the nucleus is slipping away from it. In this interpretation, the antitail becomes a tracer of the same mystery that shapes the comet's path through space. The force nudging the nucleus would naturally leave a trail of stragglers behind, and that trail, projected against the sky, can mimic a sunward feature. Then, in December 2025, the story gained another layer, with evidence that the antitail might be linked to rotation. A study analyzing images from July and August reported a subtle, repeating wobble in the jet's position angle, an oscillation with a period around 74 hours, give or take about 20 minutes. That rhythm suggests a jet source that is not perfectly centered on the rotation axis. Instead, as the nucleus spins, the jet sweeps around a small cone, and the antitail's apparent direction gently precesses like a slow, careful lighthouse beam. The wobble was tiny, only about 8 degrees. That implies the jet base sits close to the rotation pole, offset by less than 8 degrees. And that geometry matters. If the jet originates near a pole, and if the rotation axis is aligned near the sun's direction, that source region can remain illuminated for long stretches, receiving steady sunlight and feeding steady outgassing. A pole that never turns into shadow could sustain a persistent jet without the usual on and off cycle. That helps explain why the antitail looks so stable, so continuous. But then comes the sharper question. Why would the rotation axis line up with the sun at all at large distances, where the comet spent much of its approach? Its orientation would tend to be fixed, making one hemisphere long lit, the other long dark. With the sun crawling slowly across its sky at several astronomical units, the comet could keep an almost permanent day side and night side. To preserve a sunward-pointing jet throughout the inbound leg, the rotation axis would need to aim roughly toward the sun, and the odds of that happening by chance, some estimates suggest, are around 0.5%, another small probability to add to an already crowded list. After perihelion, the geometry becomes even more complicated. The comet's path was bent by about 16 degrees through its solar passage. If the rotation axis stayed fixed in space, the alignment with the sun should have been disrupted. Yet in December, the antitail remained, still roughly sunward, still narrow, still present. That implies either the axis shifted to keep up, requiring a torque, or the active source changed. Lowe highlighted this as yet another oddity. One way to preserve the sunward orientation is a flip in active regions. Before perihelion, one pole drives the jet. After perihelion, the opposite pole becomes dominant. That would require two volatile pockets near opposite ends, both close to the rotation axis, both capable of producing tight, collimated outflow. It's a geometrically special arrangement, not impossible, but unusually neat. Mainstream planetary scientists, however, emphasize how messy comet physics can be. Jets are common. Their shapes can be sculpted by cliffs and pits, by uneven ice distribution, by shadowing, seasonal illumination, and topography we can't resolve from Earth. In that view, the anti-tail may be dramatic, but not beyond nature. Steve Desch of Arizona State University has argued that some of the more exotic interpretations lean too heavily on incomplete assumptions, especially when the complex role of radiation pressure on dust is undermodeled. Dust doesn't behave like a simple spray. It can form structures, streamers, and sunward-looking features under certain geometries. And so the debate continues, with each side building models, each side pointing to the same images and seeing a different story inside the light. What no one disputes is this 3-eye atlas shows jet activity unusual enough to pull real attention from the field. For backyard observers, the anti-tail became one of the most striking signatures, a comet that didn't look like the comets we grew up drawing. Often it appeared to have multiple structures at once, a dust tail, a plasma tail, and the stubborn sunward beam. Some images even hinted at spiral patterns, the kind you might expect when a rotating nucleus vents through a fixed opening, sweeping a jet through space as it turns. And the truth is, comet jets are complicated. Many anomalies soften into ordinary physics once enough data and careful modeling arrive. 3-eye atlas may end up in that category. The anti-tail might be explained by some blend of particle size, composition, viewing geometry, and layered activity we simply haven't had reason to model before, especially for an interstellar comet this large and this active. Or it may represent something genuinely new, a behavior we've missed only because we've never had this kind of visitor to study. And yes, there is also the provocative possibility Lowe keeps on the table that the object is not merely natural, but something engineered that wears a comet's disguise. The anti-tail, on its own, proves nothing, but it refuses to be ignored. It's a puzzle with teeth, a feature that demands a mechanism, not a shrug. And even if the answer turns out to be ordinary, the question has already pushed comet science forward, forcing sharper models, better observations, and deeper humility. Because one day, 3-eye atlas will grow too faint. The sunward jet will vanish from our images, but the data will remain stored, archived, waiting for future eyes and future methods. Maybe years from now, someone will reanalyze those frames and finally see the missing step, the small physical detail that makes the wrong-way stream inevitable. Until then, the mystery stays with us. A jet pointing sunward, defying instinct, challenging explanation. One more strange signature in an object that seems determined to test the edges of what we think we know about visitors from other stars. And now, we move toward the last act of this journey. Not the end of the comet's voyage, but the end of our close. Precious window to watch it, because ahead lies one more encounter, a meeting with the giant of our solar system, and a coincidence so precise it has fueled wonder, skepticism, and sleepless debate. Farewell to the visitor, Jupiter's Hill Radius, and the final secret. Even as you listen, 3-eye atlas is already slipping farther away from Earth, its closest approach behind it, its light thinning, its path bending outward into colder space. In the months ahead, it will cross Mars's orbit again, then drift past the asteroid belt and set its sights on Jupiter before continuing toward Saturn, Uranus, Neptune, and beyond. Eventually, it will leave the sun's realm entirely and resume the endless, quiet falling it has done for ages. But before that, one more moment awaits. On March 16th, Liang Tianling Archelo, 3-eye, Atlas makes its closest pass to Jupiter, the solar system's heavyweight. a planet whose gravity shapes whole families of orbits. Jupiter's influence is so deep it can capture comets, scatter asteroids, and act as both shield and sculptor for the inner worlds. And around that planet is a boundary line with a name that matters here, the Hill sphere. The Hill radius marks where Jupiter's gravitational dominance competes most directly with the Sun's. Inside that region, Jupiter can hold objects in orbit. Outside it, the Sun remains the main ruler. For Jupiter, that Hill radius is about 53.5 million kilometers, and when researchers projected 3I Atlas forward, the predicted closest approach came out near 53.4 million kilometers, almost identical, a match within about 0.1%. In a solar system built on vast scales, that precision feels uncanny. Jupiter's orbit spans hundreds of millions of kilometers, yet the comet appears to skim the planet's gravitational boundary, as if tracing a drawn circle in the dark. Lowe estimated the odds of such a match as extremely small numbers like 1 inch 25,000 appear in the discussion, and when added to other low probability features, the coincidence becomes one more spark in an already heated debate. If the alignment is real, what would it mean? The Hill boundary is a kind of gravitational balance zone. A spacecraft placed near it could, in principle, maintain position with minimal fuel, small corrections, gentle nudges, long-term persistence, and, if a passing object released fragments there at just the right speeds, some material could be shepherded into stable configurations, especially near the Lagrange regions, where forces balance. That's the seductive speculation, a perfect place to leave something, to park something, to watch something. If 3I Atlas were artificial, Jupiter is an obvious target, not only because it's massive, but because its moons are among the most scientifically intriguing worlds we know. Europa's hidden ocean, Ganymede's size and magnetic field, Io's volcanic fury, Jupiter's radiation belts and vast magnetosphere. To any curious intelligence, it's a laboratory the size of a system. In that imagined scenario, deploying observation platforms near the Hill boundary could allow long-term monitoring of the Jovian realm without constant propulsion, without dramatic maneuvers, with patience measured in decades or centuries. It's a compelling story, but it remains a story, because there is no evidence 3I Atlas will release anything. No confirmed sign of deployable objects, no signal that it carries hardware, no direct proof that it is anything other than a natural comet on a path shaped by gravity and subtle outgassing. The mainstream view is straightforward. This is coincidence, amplified by human pattern seeking. And there is another caution. The predicted Jupiter distance depends on parameters still being refined, especially the uncertain details of non-gravitational acceleration. Small changes in those assumptions can shift projections by millions of kilometers. So the needle threading might drift as the data improve, and what looks exact today could soften into something ordinary tomorrow. We will know more as tracking continues. Telescopes will keep following the comet as it fades. Models will tighten, and in March 2026, the encounter will unfold in full view of instruments, possibly including spacecraft already at Jupiter, like Juno, and the broader network of observatories on and around Earth. If the comet behaves like a comet, that will matter. If it surprises us, that will matter even more. But regardless of what happens at Jupiter, the larger arc remains the same. 3I Atlas will keep moving outward, past the outer planets, past the last bright edges of our observational reach, and into the long, silent ocean between stars. If it survives intact, it carries with it a record of this passage: dust shed into our sunlight, gas released into our wind, tiny perturbations etched into its orbit, a brief chapter in a journey measured in billions of years. And we will be left with what we always have: light, data, memory, and the quiet realization that some visitors do not come to stay. They come to pass by, to show us how much we still don't know, and to remind us, gently, that the universe is wider than our certainty. Of course, all of this is still speculation. There is no evidence that 3I Atlas will release anything near Jupiter. No confirmed sign of deployable technology. No clear indication that it is anything other than a natural comet moving along a path shaped by gravity and gentle outgassing. For most scientists, the Hill sphere match is simply that, a coincidence that our minds can't help but highlight. And to be fair, strange alignments do happen. If you measure enough angles, distance, and timings, something will always look too perfect. That's selection bias, finding patterns after the fact that no one predicted in advance. And in this case, the details matter, because the exact track of 3I Atlas still depends on parameters with real uncertainty. The non-gravitational push has been notoriously hard to model, change the assumptions, and the forecast shifts. Different outgassing laws produce different futures, so it's entirely possible that as the data improves, the predicted Jupiter distance will drift, moving away from the Hill radius and quietly dissolving the coincidence. We'll know much more soon. Continued tracking will tighten the orbit, reduce the error bars, and reveal whether the Hill sphere alignment is genuine or just a temporary artifact of imperfect modeling. And when the encounter comes, it won't happen in secret. Ground-based telescopes will watch, and spacecraft in the Jovian neighborhood, including Juno, still circling Jupiter, may add their own measurements to the record. But no matter what Jupiter reveals, it won't be the final chapter. 3I Atlas will keep moving outward, past Saturn, past Uranus, past Neptune, and by 2029, beyond Pluto's orbit crossing the loose boundary of what we call our solar system. Then it will continue, as it has for ages, falling through the galaxy on a silent trajectory measured not in years, but in eras. It may pass other stars, close enough to feel their warmth, or far enough to remain frozen and untouched. Cosmic rays will keep striking it, slowly reworking whatever ice remains, layering new chemistry over old chemistry, turning today's surface into tomorrow's crust. And if 3I Atlas survives as a coherent body, it will carry a subtle record of this visit, the volatiles it vented, the dust it shed, the tiny nudges and bends written into its orbit. All of that will be stored in its structure like faint handwriting, and it's not impossible to imagine a distant future, a civilization millions of years from now, finding this object and reading its story backward. They might infer it once passed a yellow star with 8 planets, including one small blue world, alive with motion and chemistry. A world like ours. What would they think of us? Would they find any trace, a whisper of terrestrial dust caught in the comet's wake, a tiny contamination from our inner solar system, so slight we'd never notice it now? Would they debate? As we do. Whether the visitor they're studying was natural or crafted, these are questions without answers, a daydream stretched across impossible time. But the daydream serves a purpose. It reminds us how small our moment is, how enormous cosmic time truly becomes, and how this story does not end when the object leaves our telescopes. We are witnessing one brief chapter in a journey that may span the lifetime of the universe. And in that brief chapter, we have learned quite a lot. 3I Atlas is the third confirmed interstellar object ever identified after Oumuamua in 2017 and Borisov in 2019. It appears larger and more active than either predecessor, a genuine comet with a nucleus, a comma, and strong tails. Its likely origin points toward the Milky Way's thick disk, among older stars, and statistical work suggests it may be astonishingly ancient, perhaps 7 to 14 billion years old, making it one of the oldest cometary bodies we've ever studied. And yet, it carries a list of puzzles. An orbit aligned with the ecliptic more closely than chance seems to favor, an arrival direction that echoes the long-haunting WOW signal of 1977, unusual nickel signatures, a stubborn anti-tail that resists easy explanations, non-gravitational acceleration that may or may not line up with Jupiter's Hill boundary. Each item could be ordinary on its own. Together, they form a pattern that some researchers find unsettling. The mainstream view remains steady. 3I Atlas is a natural interstellar comet, unusual, yes, but ultimately explainable through better comet physics and a better understanding of interstellar populations. Avi Loeb and a smaller group argue for a wider frame, not certainty, but openness that alternative hypotheses, including artificiality, should not be dismissed before the evidence is fully tested. And the debate will outlive the comet's visibility. The data will be studied and restudied for years. Future interstellar visitors will give us what we lack today: context, statistics, comparison. And slowly, the field will decide whether 3i Atlas was typical or truly exceptional. For now, what remains is wonder. Something from another star crossed our neighborhood. It spilled ancient ice into modern sunlight. It was photographed by robotic explorers on Mars, watched by telescopes in Earth orbit, and observed by spacecraft on their own long journeys. It stirred controversy, and also something quieter, a renewed sense that the universe is stranger than our habits of thought. Tonight, December 19th, 2025, 3i Atlas is at its closest to Earth. About 168 million miles separate us from this messenger of deep time. And from this point forward, the distance only grows. The comet will fade and eventually pass beyond what even our best instruments can follow. So let's say goodbye, gently. Farewell to the ancient wanderer, the time capsule from the thick disk, the visitor that made scientists argue, and made so many of us look up with a strange feeling as if the night sky had become more personal. Farewell. 3i Atlas, whatever you are and wherever you came from, may your voyage be long. May your secrets be understood someday, even if not by us. We could not reach you. We could not land on you, or take a sample, or follow you into the dark. But we did something that matters. We saw you. We measured you. We questioned you. And for a few months in 2025, you reminded us what science really is, the courage to look and admit we don't yet know. Thank you for spending this time with me, for traveling through the story of 3i Atlas, from its discovery in July to its closest approach tonight. I hope the journey felt as I feel it: mysterious, beautiful, and full of that gentle uncertainty that makes the universe worth exploring. If you'd like to support the channel, please consider liking and subscribing. It truly helps these documentaries reach more people, and it allows me to keep making calm night sky stories for those who love to fall asleep beneath the stars. You can also tap the notification bell so you don't miss the next episode, and share this video with someone who might enjoy a quiet story of cosmic visitors. And if you feel like it, tell me in the comments, do you believe 3i Atlas is simply a natural comet, ancient, rare, but ultimately explainable? Or do you sense something else in the way the anomalies seem to gather? I read every comment, and I'm grateful for this community of curious minds. One gentle note before we part. Some ideas discussed in this documentary are speculative and not accepted by the broader scientific consensus. Science is an ongoing process, and our understanding of 3i Atlas will continue to change as new observations and peer-reviewed analyses arrive. For the most current picture, always rely on vetted research sources. And now, as the night deepens and 3i Atlas begins its long goodbye, let's carry the feeling it left behind, that sense of wonder you can't quite name. The universe sent us a gift from another star, a frozen fragment from before our sun was born. We opened it the only way we could, with light, with instruments, with patience. What we found was beautiful and strange and full of questions that may never fully resolve. But that is the joy of discovery. That is why we keep watching, why we keep listening, why we keep looking up. Good night. Everyone, sleep well and let the story drift away. Tonight, we followed a traveler made of ice and starlight, not to solve every mystery, but to sit beside it, quietly, as it passed through the world of questions. If your thoughts are still awake, let them loosen, like dust in a gentle solar wind, floating farther and farther, because from here, 3i Atlas will keep going, past the outer planets, into colder darkness, back to the long silence between stars, and we will remain here, beneath our own sky, with the one thing science always gives us first, the chance to notice, to wonder, to learn. Thank you for spending this quiet time with Bedtime Talks, and if you'd like to, support the channel. You can like, subscribe, and share this episode with someone who might enjoy falling asleep to the universe. Now, take one last slow breath, feel the night soften around you, and let sleep arrive, gently. Good night, sleep well, and may your dreams be full of stars, quietly drifting far beyond the edge of morning.